Welcome to The Explainer. Today, we are diving into a really fascinating idea. What if we stopped treating economics like a social science and started treating it like a hard engineering discipline? With things like forces, momentum, and friction.
It kind of sounds like the start of a bad joke, right? I mean, on one hand, you have a flywheel, this heavy, spinning wheel that stores energy. And on the other, you have the price of oil, a number that's constantly changing. What on earth could possibly connect these two things?
Well, the answer is a pretty groundbreaking way of thinking called economic engineering. The whole idea is that the same fundamental laws that govern a flywheel or an electrical circuit can actually help us understand and maybe even design entire economies.
To really get our heads around this, we've got to go back to basics. We're talking one of the very first things any engineering student learns, the universal concept of force.
Okay, so first up, you've got Isaac Newton's motive force. It's pretty straightforward, right? It's the push or the pull that makes something speed up, slow down, or change direction. It's literally what gets things moving.
And it's not just in mechanics. In electrical engineering, you have what's called electromotive force, which we all know as voltage. It's the force that pushes electrons through a wire. So you're seeing the pattern here, right? A specific kind of force creates a specific kind of motion.
Which, of course, brings us to the big question. An economy is a system in motion. You've got money, goods, and services flowing all over the place. So what's the force driving all of that?
And this is the absolute core of economic engineering. The economic motive force isn't some physical push. It's us. It's a human want, a desire, an incentive. These are the invisible forces that are actually pushing and pulling our entire economy.
And once you define that economic force, well, that's when things get really interesting. You can suddenly unlock this whole set of analogies that let us map the principles of engineering directly onto the world of economics.
Okay, now this slide. This is where it all clicks into place. It totally reframes how we think about the economy. We just talked about the forces, that's the top line. But look at the next one. In this model, price isn't just a number, it's momentum. And velocity? That's the flow of goods. This is the big aha moment. Let's break down a few more of these, because this is really cool. All right, let's start with mass. In physics, mass is just inertia, right? It's how much something resists changing its motion. Well, in economics, that's demand stickiness. Just think about the world's demand for oil. That flow has an enormous inertia. It's incredibly hard to change it quickly. You need a huge economic force, some massive crisis or incentive, to really change its velocity.
Okay, what about a spring? You compress a spring, it stores energy. Well, an economic inventory, like a warehouse that's just jam-packed with stuff, it does the exact same thing. When that warehouse gets too full, it's like a compressed spring. It pushes back by creating pressure on the market to lower prices and sell things off. It releases that stored potential.
And finally, we've got dampers. These are the things that create friction, that slow a system down. The economic version? That's transaction costs. Every single broker, middleman, fee, or tax in a deal, it all acts like friction. It drains energy out of the system, which reduces the momentum. And in our analogy, that means it reduces the price.
So now that we have this cool new engineering toolkit, we can go back and look at maybe the most famous idea in all of economics, supply and demand, but in a completely different light.
We all learned this in school, right? You've got the demand curve going down, the supply curve going up, and boom, where they cross, that's your equilibrium price. It's treated like a static, unchanging snapshot.
But economic engineering says, hold on, let's just throw that static picture right out the window. That graph isn't a picture of a single point in time. It's a dynamic system. It's showing the relationship between momentum and velocity, just like you would in a physics problem. It's always in motion.
And this is the key. As the lecturer from our source material put it, you have to stop thinking about a single price determining equilibrium. It's not. It's determined by price changes, and price changes are the result of forces being applied to the system.
So what is a true economic equilibrium? Well, think of it like a perfectly balanced game of tug-of-war. It's the point where the wants of all the consumers on one side are perfectly balanced out by the incentives offered by the producers on the other. The net force is zero, and that rope is held perfectly still.
So if this whole analogy holds up, it's a huge deal. It doesn't just give us a new way to describe how markets work, it might give us a new way to actually build them. I mean, if markets really are just incredibly complex engineering systems,
then suddenly the entire toolkit of modern engineering could be used on them. You could use circuit theory to model how markets clear, control theory to create more stable prices, maybe even thermodynamics to understand risk. The possibilities are kind of mind-boggling.
And that really leaves us with a fascinating final thought. A physicist's job is to describe the world, but an engineer's job is to build a new world. So if markets really do behave like circuits, could we one day move beyond just analyzing our economy and start actually designing a better one? One that's more stable, more efficient, and more resilient to shocks. It's a really powerful idea to think about.